the wedge representation. According to this structure, the thick or dark line indicates a CH bond lying above the plane of the paper, that is projecting towards the observer. The normal line represents carbon-hydrogen bond lying in the plane of the paper, while the two dotted lines represents the CH bonds lying below the plane of the paper. This representation describes the actual positions of various atoms present in the molecule in space, hence it is called a spatial formula. Next, the graphic representation. This is a two-dimensional representation of methane molecule. Although this formula does not reveal the two tetrahedral geometry of the molecule. This is most commonly used because it is very easy to draw. Next, the chemical properties of alkanes. Alkanes are extremely stable and inert substances, and this is due to the following facts. A. There is a small difference in electronegativities of carbon and hydrogen, which is 2.60 and 2.10 respectively. With the result, the bond electrons in carbon hydrogens are practically equally shared between the two atoms, and hence the carbon-hydrogen bond is non-polar. Further, the carbon-carbon bond is completely non-polar, and therefore the electrophilic and nucleophilic reagents find no site on the alkane molecule. They are almost non-polar and strong bond, non-polar and very strong bond. Second, since carbon-carbon and carbon-hydrogen bonds are strong bonds, carbon-carbon bond energy is 83 kilocalorie per mole, carbon-hydrogen bond energy is 98.8 kilocalorie per mole. Alkanes having only these two types of bonds are unaffected by acids, alkalis and oxidizing agents under the normal conditions. However, alkanes do show some reactions under special conditions, and some of the important reactions of alkanes are the first reaction, the halogenation, that is replacement of hydrogen atom by halogen atom. Alkanes react with halogens, that is chlorine, bromine, in presence of sunlight, ultraviolet light, or in dark at high temperature of around 250 to 400 degrees centigrade to form the corresponding substituted product. The reaction of methane with chlorine undergoes continuous halogenation to give methyl chloride, methylene chloride, trichloromethane, commonly called as chloroform, and carbon tetrachloride. It is difficult to stop halogenation at CH3Cl level when equimolar amounts of CH4 and Cl2 reacts. A mixture of all four products is formed. However, the yield of CH3Cl can greatly be improved by using excess of methane. This is because the chances of a chloride to collide with methane molecule rather than with a chlorinated derivative are enhanced. Bromination also takes place like chlorination, but of course slowly and at a high temperature. Since hydrogen iodide formed during iodination reduces the product back to methane, iodination is reversible and hence must be carried out in presence of strong oxidizing agent like iodic acid, that is HiO3, nitric acid HNO3, or mercuric oxide HGO, which destroy the hydroiodic acid and thus prevent the reversibility of the reaction. The reaction CH4 plus I2, it is reversible and forms CH3I plus Hi. This Hi reacts with HiO3 to give iodine plus water. Iodo compounds are obtained by treating chloro or bromo derivatives with sodium iodide in acetone. It is a halide exchange reaction. The reaction is C2H5Br plus NaI. It gives C2H5I plus NaBr.